So the only difference in solving linear inequalities compared to equations is when we multiply or divide by a negative number the inequality symbols reverse. So that means if we multiply or divide an inequality by a negative number, our inequality symbols are going to reverse. So in other words, a greater than will turn into a less than, and a less than will turn into a greater than. So let's go ahead and take a look at our first example. So we want to solve and graph the solution set. So we have x minus 3 is less than 4x plus 9. So we minus 4x and we minus 4x. That gives us negative 3x minus 3 is less than 9. And we add 3 and we add 3. And that gives us negative 3x is less than 12. And now, in our last step, we need to divide both sides of our equation by negative 3. And when we do so, we get our x, and 12 divided by negative 3 is negative 4. But since we divided by a negative, we had to reverse our inequality. So our less than symbol reversed and became a greater than symbol. So now we wish to graph this. So we have x is greater than negative 4. So on our number line, we'll just go ahead and mark our important number, which is negative 4. And since we have a greater than symbol, and not a greater than or equal, we're going to put a rounded parenthesis, and recall that this means not included. So just to clarify that a little bit, we also have another notation that we want to take note of. Note, a hollow circle also means not included. So it would look something like this. So if we had a hollow circle and an arrow, or this, both of these are not included. And if we had a filled in circle and an arrow, or a square bracket and an arrow, both of these mean included. So these are the same notations that we used with interval notation. We also have an alternate notation where we have the filled in circles and the hollow circles. So just be aware that they exist and that we can do them. All right. So we had that our solution set was the set of all x's such that x was greater than or equal to -4. It turns out that we can resolve this problem graphically. So to aid with this, we're going to do it graphically. I'm going to label each side of my inequality. So I'm going to call x minus 3 y1, and I'm going to call 4x plus 9 y2. If I grab my graphing device, and I press my y equals, so my y1 is going to be x take away 3, and I press enter, and then my y2 is 4x plus 9. So in y1 I typed my x minus 3, and in y2 I typed 4x plus 9. So now if I go ahead and graph this, it now graphs y1 and y2 on my same axis. So now while looking at my picture, so to help, this is my y1, so I'll label it in blue, and my y2 is the 4x plus 9. And we have the following statement then. So we have y1 is less than y2. And what this is asking us to do then is the following. Is we want to answer the following questions. So for what values of x is the blue graph y1 below the red graph. But remember, we're looking for the x values. So they intersect right here, and using the eyeball metric, it looks like it's at about x equals -4. But let's use our calculator once again to find that exact value. So we grab our calculator, and we're going to go back into our calculate menu that we used not too long ago. So we go to calculate. Before we use 0, this time we're looking for the intersection. So we go down to choice number 5, and we press enter, and it's going to ask us 3 questions again. If you only graph 2 things, it's really easy. You just hit enter, enter, enter. First curve, second curve, guess. Just press enter, 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 and it will find the intersection of those 2 things. And when we do so, our calculator should have given us something that looks like this. And indeed, it does confirm what we thought, that our x value was -4. So now we're ready to answer our question. So for what values of x is the blue graph below the red graph? Well, it's above until we get to x equals 4, and then the blue graph stays below for all of these. So then our solution would be all of those values right here. And notice that this is x is greater than -4. Well, does that look familiar? Oh, that's exactly the solution we got up here. So this is the way we can visualize this graphically. When we graph each of these, the question that it's asking is, for what values of x is y1 below y2? In this case, I color-coded them to help make it a little more apparent. But that is the idea, graphically, what's happening.
Would it kind of, in a sense, be as if were they joint because they pretty much cross?
The next thing we need to talk about is the domain of a radical function. So if we have a radical function, it looks something like this. We have f of x equals the square root of some function. And remember that the square root symbol's technical or official name is a radical. The thing that lives inside the radical, or the inside bit, is called the radicand. So to find the domain of a radical function,
Professor, is that a p that's next to the x inside of the radical? Okay, thank you.
we solve the inequality radicand is greater than or equal to 0. So to find the domain of a radical function, we're going to solve the following inequality, that the radicand has to be greater than or equal to 0. The solution is to the inequality is the domain. All right, so we want to determine the domain of the following function. So we need to identify our radicand. So the radicand is just the part that is underneath the radical. So that plus 4 on the outside isn't anything. So we need to solve radicand is greater than or equal to 0. So in this case, our radicand is 8 minus 2x is greater than or equal to 0. So now to solve this inequality, we minus 8, we minus 8. We get negative 2x is greater than or equal to negative 8. We divide by negative 2. We divide by negative 2, and we get x, and we have to reverse our inequality symbol because we divided by a negative. So it becomes x is less than or equal to positive 4. So then the domain is from negative infinity up to 4, but since we have the or equal to, we put on a square bracket, and recall that that means that it's included. And we have, the fact that it's included comes from that we have the or equal to on our inequality symbol. So that would be the domain of our radical function. So for our u-try, we identify our radicand. So our radicand is the stuff underneath the radical. So in this case, it is x minus 3 over 2 has to be greater than or equal to 0. So to solve, we add 3 over 2 to both sides, and we get x is greater than or equal to 3 over 2. So then the smallest value that it can be is 3 over 2, and that's included, and x has to be bigger than that, so it goes all the way up to infinity. And that would be our domain for that radical function. All right, we have time for some definitions and maybe an example, and then we'll go ahead and stop. So the next thing we want to talk about are compound inequalities. And compound inequalities come in two types. They come in the type and in the type or. So the first one that we want to talk about is the and type. So let's take a look at an example. So let's imagine that we have two inequalities. We have x is less than 6 and x is greater than negative 1. So we have two inequalities, and they are just connected by the word and. So if I were to create a number line, so I have my negative 1 and I have my positive 6, and I'm going to color code these. So if I start with x is less than negative 6, well, that would be here, and if I were to shade that on the number line, it would be everything to the left of 6. And then I have my blue inequality now. So x is greater than negative 1. So I'd go to negative 1, but then I would have to shade everything to the right. Well, and means I need both of these statements to be true. And in this example, when you mix yellow and blue, you get the color green. That is the representation of the and type inequality. So then our solution to that and would be right here, and it's going to be from negative 1 to 6. The formal name for an and is intersection, which means where do the two sets overlap? And the values that they have in common, or the values that where they overlap, are in between negative 1 and positive 6. So that is a visual representation of an and type inequality. Mathematicians work very hard at being lazy, which means we want to write as little as humanly possible. So instead of writing an inequality like this, where we write x is less than 6 and x is greater than -1, we can write this as a compound inequality. So what I mean by that is if I start with my part in blue, I have -1, and we notice that the inequality symbol opens away from -1. -1 is less than x. And then if I look at my yellow inequality, I have x is less than 6. This inequality is the same as what we wrote above. It is two different ways to write the same thing. One of them, we just held them together with the conjunction and, but if we look at just the left-hand side of that, it says that -1 is less than x. And if we look at the right-hand side of this, it says x is less than 6. So it is just a more compact way to write that. So this compound inequality is often called a three-part inequality. All right, so we're going to go ahead and, so just to remind us, we had been talking about and type inequalities, and when we have something of this form where it has three algebraic expressions connected by inequality symbols, this is a compound inequality of type and we often refer to this as a three-part inequality. So example 3 is also an example of a three-part inequality. So when we are trying to resolve this, the key idea is the following. If we do something to one part, we must do the same thing to all other parts. And this is really just a generalization of the idea. If we do something to one side of an equation or an inequality, we have to do the same thing to the other. Well, now in terms of sides, instead of just having two sides, you can think of it as we have three sides. So if I do something to one part, I must do the same thing to all parts. So if we start with -3 is less than 2x take away 5 is less than 7, we need to do the same thing to all three parts. So we want to get our x in the middle by itself. So to do so, we would start by adding 5 to all three parts of our inequality. Now that would give us -3 plus 5 is 2 is less than, those reduce out. We have 2x, and 7 plus 5 is going to give us 12. So then we further wish to isolate x, so we're going to divide all three parts by 2. And finally, at the very end, that leaves us with 1 is less than x is less than 6. So after doing the same thing to all three parts and resolving, we'll notice this ends up exactly in the same form as the example that we finished on last time. So it tells us x is trapped between these two values. So in this example, our x is trapped in between 1 and 6. So if we mark our two important parts, we have our 1 and we have our 6. If we want to do it the super long way, we could do, our yellow would be x is bigger than 1, which would mean we would shade here. And then if we did this part, it says x is less than 6. If we shade that in blue, that's this part right here. And we see that our and is where those two things overlap. And that would give us that x is trapped between 1 and 6, which is what we saw. But that was really overkill in this, because if we look right here, we notice that our x value, we can see x had to be less than 6 but bigger than 1, which was exactly the part that we saw here in green. So we can formally look at it as the and, or the three-part inequality will show us exactly where the solution is going to be when we do this. All right, I'm going to group our next two u-tries together, so I'm going to move to example 4, and then we'll do the two u-tries at the same time. So if we take a look at example number 4 now, we're going to be looking at an OR type inequality. So to resolve an OR type, we basically are going to solve each of them separately and then just put the two solutions together. So when resolving an OR type, we're going to just focus on each part separately. So if we just look at 2x minus 5 is less than negative 7, we're going to solve it just the way that we did. So a question came up on the previous part wanting to know if since the inequality symbol here is a less than, wouldn't we shade to the left? But we have to be careful, because when we look at this part right here, we have 1 is less than x. So our inequality symbol is opening towards the x. If it helps you visualize it, as long as you preserve the orientation of the inequality symbol, it's still opening towards the x. This says x is greater than 1, which would be the same thing. So we have to be a little bit careful, because we're used to writing our variables on the left and our numbers on the right. And so sometimes we assume that that's always going to be the case. But these two things are equivalent, because this says 1 is less than x. So that would be that we need x values that are bigger than 1 because of the way that this is oriented. And when we switch it, it makes it a little bit more apparent. But so we would still need to shade to the right. Okay. So back to example 4, when we have an OR type, we're basically going to write down each of the inequalities and just solve them separately. So when I look at this left-hand side over here, I'm just going to ignore the x plus 3 is greater than 8 and focus on this. So to isolate x, the first thing I'm going to do is add 5 to each side of my inequality. And that gives me 2x is less than negative 7 plus 5 gives me 2. And then I divide by 2 and I divide by 2. And that gives me x is less than 1. And now that I've resolved this, I'm going to ignore it and just go resolve the one on the other side. So then I would go minus 3 and minus 3. And that gives me x is bigger than 5. So now I would have these two inequalities. And when I have an or statement, I only need one of these two things to be true. So unlike in the previous example where we had ands we were looking for both yellow to be true and blue to be true. And when you mix yellow and blue, when they're both true, we get our and, which is green. For an or statement, only one has to be true, so we're only going to use one color. We mark our significant numbers, which are 1 and 5 respectively, and the first one says x is less than 1, so we shade everything to the left of 1, or x is bigger than 5. And since only one of these inequalities need to be true, this gives us two different branches to our solution. So we're going to have in yellow from negative infinity up to 1, not included, unioned with 5 to positive infinity, not included. So the union symbol is really just our mathematical abbreviation for or. So when we see union, what we're really talking about is the word or. So that's just our symbol for x is in negative infinity to 1 or from 5 to positive infinity.
Mr. Peterson, wouldn't it be -1 since 7 was larger than 5 and 7 was negative?
Yes,
9?
because I totally lost a minus sign. Yeah, thank you. Because -2, yeah, so perfect. So, yeah, I totally lost a minus sign. So -7 plus 5 was -2, and -2 divided by 2 is -1. Absolutely. Thanks for keeping me honest. I told you on day 1 that you'd see me do 2 plus 2 equals 5. This time it was -2 divided by 2 was +1. So perfect. And that would be our solution. So, okay. All right. So now it is your guys. So the best way to do U try number 3 is to clear all of our fractions by multiplying by the LCD. So if we want to clear the fractions by multiplying by the LCD, so in this case our LCD is pretty simple. It's just 3 because there's only one fraction. If we multiply each part of this by 3, we have 3 times -4 is -12. Here the 3 and the 1/3 reduce out, so we would get 2x plus 1 is less than 6 times 3 is 18. So when we do this, we now have an equivalent problem where we're not going to have any fractions until the very last step. So then now we need to resolve this, so we will -1, -1, -1 from all 3 parts. That gives us -13 is less than 2x is less than 17. We divide by 2, divide by 2, divide by 2, and we get -13 over 2 is less than x is less than 17 over 2. And so this is our and type, so we mark 13 over 2 and 17 over 2, and we don't include our endpoints, and we graphed our solution to that inequality. All right, for example 4, or you try number 4 rather, we're trying to resolve this inequality for x as well. So we start by solving each of them independently. So we add 5 and we add 5, and that gives us x is less than or equal to, and we could get a common denominator, or if we're feeling particularly lazy, we just type it in. So we go negative 1/2, and then we would add to it 5, and that gives us 9 over 2. Or, and then we do the same thing, we're going to add 5 and add 5. So then this time we would do our positive 1/2 plus 5, and we'll get 11/2. So then this time we have to be a little bit more careful, because we notice here we have a less than or equal to, and then we have just a less than. So when we make our number line, we have 9/2 and we have 11/2, and we are going to include at 9/2, so we get a square bracket, and then we don't include at 11/2 because we don't have the less than or equal to on the other side. We have just a strict inequality at greater than. So that would be our solution set in terms of a graph, and just remember square brackets for our included when we're doing these. All right, so we have one last example from this section. So example number 5. So for example number 5, we have Acme Movers charges $30 plus $20 per hour to move household goods across town. Hank's Movers charges $35 per hour. For what length of time does it cost less to hire Hank's Movers? So the idea here is, once again, we're going to be using our linear model, which is y equals mx plus b. And we've talked about how m is our slope, and our b value is the y-coordinate of the y-intercept. In terms of application problems, and we've mentioned this before, our slope is our rate of change, and the y-coordinate of our y-intercept is our starting value. So in terms of what we're going to be looking at here, we can still use our same model, but we want to think of these as terms of rates, and where do we start? So for our starting value, in our first one, our Acme Movers, to start, they charge us $30 just to show up, and then their rate of change is $20 per hour. So for Acme Movers, our cost is going to be our rate, which is $20 per hour, times the number of hours, so that's our x, plus the starting amount. Similarly, when we look at Hank's Movers, this time, for Hank, we have our rate of change is $35 per hour, but Hank doesn't charge you anything to just show up and start moving your stuff. So he charges you only $35 per hour. So those are our two equations that represent the cost for each of these movers. The question we wish to answer then is, for what length of time does it cost less to hire Hank's Movers? So what we want is x when h is less than a. Well, our h is 35x, and we want to know, well, when is that less than a? And a is 20x plus 30. So to resolve that inequality, we minus 20x, we minus 20x, and we get 15x is less than 30. And we divide by 15, divide by 15, and we end up with x is less than 2. So this tells us then it will cost less to hire Hank's Movers for 2 hours. So these types of problems actually come up quite a lot. If you've ever hired like a plumber or anything like that, they generally charge you a service fee to show up at your house, and then they're going to charge you by the hour for whatever services they're going to perform while they're there. So you can compare prices by doing these different things to help us see what they're worth.